Okay, good morning. So here we are, I guess, Monday after homecoming. So it's almost like we're getting into the home stretch. We hit November, and then it'll be December before we know it. And what we're working on here is last class we finished up Chapter 6. So Chapter 6 was all about these spherical mechanisms. And we looked at everything from triangles to heptagons. Again, for the heptagons, the spherical mechanism was 4 degrees of freedom, so I had to give you 4 thetas, and we solved for the other 3. And the reason we're doing all that is, we're really trying to do reverse analysis of manipulators, but given the desired position orientation, we're going to close the loop. We're going to turn our 6 degree of freedom robot into a 1 degree of freedom closed loop mechanism. And when we go to solve that 1 degree of freedom closed loop mechanism, we need to get a whole bunch of equations that relate alphas and thetas and things like that. So we made equivalent spherical mechanisms and did a whole bunch of analysis. So today we're going to start off on Chapter 7. So that's actually the Group 1, the 3D spatial mechanisms. So again, if I had a manipulator such that when we closed the loop, it turned into a Group 1, that would fall into this chapter. And we're going to find that they're really easy based on what we did in Chapter 6. Also, I guess administrative stuff, I put on the edge page here the date for the next test. So we're looking at Friday, 8 November. So it's a little bit further back. I think people had mentioned that the week before there was a lot of other stuff going on with classes and tests, and so there's no problem to move that back. It's going to cover the material through Chapter 7. And the other thing I did today is I posted a homework. So let's take a look. Out of Chapter 7, there's a problem 7.3. Oh, and I can't spell November. So let me go ahead and fix that before I forget. And OV, save, and let's update it. That's going to bug me for the whole hour if I don't fix it. Let's see. Yep. So for that Friday, the week before the test, and again, I'll get the solution posted over here. Okay, so Chapter 7. Chapter 7 is pretty good stuff because we're going to go back to the 3D spatial mechanisms. So we're going to look at a couple of cases. And we're going to see that to solve that, and what I mean by solve that mechanism is it better be a 1 degree of freedom whose equivalent spherical mechanism is 1 degree of freedom. And we'll go ahead and we'll write down exactly what are we given, what are we looking for, but we're going to find that this problem is going to go pretty simple based on the work we did in Chapter 6. Okay, so on the left, if we take a look at this and we check the mobility, it better be 1 degree of freedom. So for the closed loop mechanism, the mobility equation, because the number of links equals the number of joints, the mobility was the sum of the freedoms of the joints minus 6. So I've got 1 freedom, relative freedom on the revolute. There's another one that gives us 2. Oh, that has 2 freedoms, so it's 4. 1 freedom is 5. 2 freedoms, so you get 7 minus 6 is 1. So this definitely is 1 degree of freedom. And when we go to the equivalent spherical mechanism, I know theta 3 because of the prismatic, but the cylindric joints map as revolute joints when you go to the spherical mechanism, and the revolutes map as revolutes. So if I look at the thing over on the right, the mobility turned out to be the freedoms of the joints minus 3. So we've got 4 revolutes that can move. 4 minus 3 is 1. So this 3D spatial mechanism is definitely one of the group 1s, which is what this chapter is all about. Chapter 8 is going to do the group 2s, and then 9 and 10 are going to do the group 3s and 4s. So here's the planar representation of the 3D mechanism, because I like to draw that a lot easier than to try to draw that. So if we take a look at it, we can see that, yeah, the prismatic is up here at the third, the cylindric, et cetera. So what exactly is our problem statement? I'm going to go ahead and put this on the board. That way we can work our equations and stuff. But for this particular spatial mechanism, we're going to be given all the alphas. So that's alpha 1, 2 through alpha 5, 1. And we're given the link lengths, right, based on our choice of S vectors and A vectors that are out there. Okay, when I look at the mechanism, again, this is the 3D mechanism. Where the revolute joints are, we know the joint offsets. So I'm going to say S5 and S1. That's where the 2 revolutes were. I guess it would help on the board, because I keep looking at the picture there. Let's go ahead and put the picture of the planar representation. So we've got a revolute, cylindric, and the prismatic is up there on 3. Also, because of the prismatic, I know theta 3. That's always going to be a constant. And I think that's it. Yep. Oh, it's a 1 degree of freedom device, so I have to give you one of the inputs, or one of the angles, and we're going to go ahead and say theta 5. I'm never going to switch this up and say, well, the input is, for example, this S4. I'm not going to do that because, right, we're trying to do reverse analysis problems. When we close the loop, remember on when we had the 6 revolutes, we knew theta 7 was one of the closed. You're going to know one of the thetas. So we're always just going to do that given one of the thetas on these problems. I'm not going to switch it up and say, oh, I'll give you S4. You should be able to solve it, but yeah, we're not going to do that. Okay, so what do we have to find? We have to find all the remaining variable parameters. So there's theta 1, theta 2, theta 4. Let's see, I need the joint offset because of the cylindric at S2. I need to get the joint offset because of the prismatic at the 3rd joint. And the cylindric is over there. So that's exactly what we're given, what we're looking for. And based on this, we have to go ahead and, see how are we going to attack it. It turns out for all the group 1 mechanisms, there's going to be 2 solutions. There's going to be an A case for all 6 of these numbers and a B case. Okay, so this is the planar representation of the 3D mechanism. Let's draw the planar representation of the spherical mechanism. And I'm going to circle theta 5 because that's given. I'm going to circle theta 3 because that's where the prismatic was. And then these all, map as revolutes, these other ones that are over here. So it turns out that the reason that these are going to be so easy is because the equivalent spherical mechanism is 1 degree of freedom. We're going to be able to solve that based on what we did in chapter 6. We're going to get an A and a B case. We're going to be able to get all the angles. So we're going to get theta 1, 2, and 4 A case, theta 1, 2, 4 B case. And then we do have to learn how do we get these values, but that's the new part in this chapter. Okay, so based on what we did, the only question is who do we want to solve for first on the joint angles? And I think in the book I even had this labeled where it might have called this the input angle and this was called the output angle. But the reason is a lot of times on these mechanisms where one of the links is fixed to ground, your motor is connected to ground and what you're trying to control is the other one. But there's no real meaning. I mean, I kind of wish if I go back to 1998 and not use the word output angle. There's nothing really more special about that angle than the other two. It just turns out that that's the one that I decided to go for first. So if I look at this picture, again, I'm hoping the equation is going to just jump right off the page. All right, we're going to go into the toolbox for the pentagon and look for an equation that has theta 1 as the only unknown. And when I look at that, I know it's a cosine law. It's okay to have theta 5. It's okay to have theta 1 because that's what I'm looking for. But I don't want to make a fundamental and go 5, 1, 2 because I don't know 2, so I'm going to stop. And it turns out 5, 1, I can go Z3 or Z3 bar. So if we go to the toolbox, we're going to find that in there. Let's expand Z51's definition is S, and there's no bar on top here, although you have to be careful with that. XS plus YC. Plus a cosine 1, 2, Z5, and then I'm going to say minus Z3 bar equals 0. And again, where the toolbox really paid off is we could go in and write down this equation with confidence. I don't have to try to generate it from first principles, which, holy cow, would have been terrible. It would have been a lot of work. Okay, our unknowns are over here, so we're going to factor that into S12Y5 C1 plus S12 X5 S1 plus whatever's left over. And based on what we're given, I know all the alphas. I know theta 5, so these are all going to evaluate to numbers. So we get our kind of classic A cosine plus B sine plus D equals 0. And we know there's going to be, for the given theta 5 and theta 3, there's now a theta 1A. And again, I didn't have to solve for theta 1 first, but that's the one that I picked. So boy, based on what we did in chapter 6, it's almost trivial. So a lot of times what we'll say is in these group 1 spatial mechanisms, the problem decouples. You're able to get the joint angles based on what we did in chapter 6, and then we come in and go for those. All right, so next we need to get the corresponding values of theta 2 and 4. So I know I need to get the sine and cosine of 2 and the sine and cosine of 4 for the A case and the B case. So I'm going to need 2 equations. I could dive in all over the place in the toolbox, but again, I usually just look at the buddy equations. So it's going to be an x, because there's not enough subscripts to be fundamental, so it's going to be a subsidiary. And when I memorize those, it turns out 5(1), it's going to be 3(2). And you can double check in the appendix that that's in there. We're going to expand the definitions of x32, xc2 minus y3 bar s2 equals x51. I'm going to move that minus sign to the other side and expand that, xs plus yc. And again, here's our unknowns. So we got 2 linear equations and 2 unknowns, just like the previous chapter. We're going to take the given theta 3, turn those into numbers, the given theta 5, and theta 1a. So for the A case, I have 2 equations, 2 unknowns. I'll solve for the sine and cosine of theta 2. Same 2 equations. I'll put in the given theta 5, the given theta 3, and then the B case of theta 1. I'll get new numbers over here, solve 2 equations, 2 unknowns. I'll know the sine and cosine. Boom. So far, it's kind of like a review of chapter 6. I mean, it's solved for the angles is going to go pretty easy for us. Okay. 1 angle to go. I know that, again, when I was doing this stuff, sitting in the back row way back when, and it was closed book, oh my goodness, I think he did let us have the appendix, though. But I looked at the other buddy equations. I knew that z51 equaled z15, so I'm going to look at x15 and y15. And again, there's not enough to be fundamentals. 1,5 is going to be 3,4. We're going to expand x34. I'm going to move that minus sign over to this side, minus y15, expand that, xs. And again, here's our unknowns. We're going to take the given theta 3, turn those into numbers, take the given theta 5 and theta 1a, numbers, solve 2 equations, 2 unknowns for the A case. Then we're going to take those same 2 equations, put in the given theta 3, the given theta 5, and theta 1b, get new numbers on the right-hand side. Solve 2 equations, 2 unknowns, get the sine and cosine of theta 4 for the B case. And boom. So on this group 1 mechanism, this is what's going to happen every time. We're going to be able to solve for the A and the B case of the joint angles based on the material we did in chapter 6. Okay, so what's left for us is to get for the A and the B case, what are these distances, right? What are those joint offsets where the cylindric and the prismatic joint were? So that's the new part here, and it's really not going to be hard. What we're going to do is we're going to start on the 3D mechanism. Let's go back to this picture. I'm going to start here, and I'm going to walk, I'm going to start actually right there. I'm going to walk the distance S1 along that vector. The distance, I'm going to say that's A12. I didn't label it, but that distance along the A12 vector. That distance along the, I'm going to walk all the way around the mechanism and come back to where we started, and we're going to equal the 0 vector. So if we write that down, I'm going to have the S1 distance times the S1 vector plus the A12 distance times that vector, plus S2 plus A23 plus S3 along that unit vector, plus A34 plus S4 plus A45 kind of wishing I would have put one more term up top here, but we'll make it. Plus S5 plus A51 times A5. And finally, I get the zero vector. Right, we're going to walk all the way around the loop of that mechanism. So I know I've got true equation. And when I look at these terms that are up here, the S's and the A's, those distances, all the A's are given because those are link values. And for the S's, I do not know this one because that's where the cylindric was. I don't know this one because that's where the prismatic was. And I don't know this one. So we've got three unknowns in that equation that we need to solve for. So we're going to show you really a couple of ways to attack this. The first one is pretty basic. It says, what if I go ahead and, like I wrote down the vector loop equation, but I haven't said what coordinate system I'm going to evaluate all the vectors in. And if you remember for the Pentagon in the appendix, we gave you all the vectors in 10 different coordinate systems. I'm just going to pick one of them. Suppose I say, let's evaluate them all in the first. Oh, all in the first. Oh, I put the one in the wrong place there. One, the first, and the first. Right? Because I have to have them, if I add these all together, they all have to be evaluated numerically in the same coordinate system. I can't evaluate this in the first and add it to that, evaluate it in the second. And I could have picked any of the 10, but let's see, what have I got here? So here's out of the appendix, there's the first set. Oh, and I highlighted in red, what the three unknowns were in the equation. So, okay, here's, S1 evaluated in the first, 0, 0, 1. Here's A12, 1, 0, 0. So it's like brute force. I just went ahead and took this work that was in the appendix. Granted, the S5 term, it is more complicated, but, so be it. So I evaluated all the vectors in the first coordinate system, and then I looked at these vectors and said, for the A case, so I had, what was it, theta 1, 2, and 4 is what we solved for. Let's see. I've got theta 1 A case. I've got theta 2 A case. I've got theta 4 A case. I've also got theta 5 was given and theta 3 was given. That's where the prismatic was. So if you look at it for the A case, I know all the angles. Okay, 0, 0, 1. Oh, I know all the alphas. Okay, this has theta 2 in it, theta 2, and this is kind of lying to us. It only has theta 2 in it, but hey, theta 2 for the A case, that's got theta 2 for the A case, so those are all going to be numbers. For the A case, these are all going to, granted there's a lot to expand, but right, for the A case, I am going to know the directions of all those vectors because I know all the angles. And then what do I have? I have three linear equations and three unknowns. So it's a lot of work, right, to evaluate all those vectors. And I didn't have to pick the first coordinate system. I could have done it in any of the coordinate systems, and I would get the same answers for those three scalars, S2, S3, and S4. Then, so at this point, I'm going to say, wow, from the three equations, three unknowns, we can go to our solution tree and say, yep, I got S2 for the A, 3 and 4, S3 for the A, and S4 for the A. Then I'm going to go back to those same equations, and we are going to put the B case angles. And again, these are all for the B case angles. They're all going to evaluate to numbers, and I solve three equations, three unknowns, and I get those, distances, the B case. So again, it's a lot of work, and when you're writing the program, right, there's all these possibilities to make a little typo mistake and things, but in general, it's three equations, three unknowns, and boom, for the A case and the B case. And they just solve out. Let's see, I'm trying to remember if there's any, there's one other story we're going to tell about this. Okay, so I'm going to get rid of these ones up here for now. And what we did, there's nothing wrong with what we did. We're just going to show sort of another way to attack this problem. We're going to say we still have this vector loop equation that's true. You know what I might do? Here's another way to attack it, is what if I took every one of these vectors in here, and what if I did a dot product with, I want to see which one I did in the book here. Oh, okay. Oh, let me clean this up too. What if I did a dot product of all of these with A34? So I'm going to say dot A34, dot A34, right? Dot A34, dot A34. And I'll tell you what in a minute why did I pick A34. Dot A34, dot, and if I was thinking I would have left a little more room on the board here to add these dots so they didn't have to look quite as crazy. Now over here, when I do dot the A34 vector, I'm going to get the zero scalar, right? So if we do any of these dot products, you get a scalar value. So we're not going to have three equations, three unknowns anymore, but we're going to have one equation and three unknowns. But the reason I picked the A34 is I knew it was perpendicular to S3. So I know that's going to go to 0. And I know A34 was perpendicular to S4. So I picked the A34 in this case on purpose because when I do the dot product, I'm going to get one equation and one unknown. Now, is this better than three equations, three unknowns? I don't know. It's still a lot of work. But usually this is the way I do it. I just like having that one scalar equation. Okay. Oh, and I know this one's going to go to 1, right, because they're a unit vector dotted with itself. So now we have to do all these dot products. Now, when we do the dot products, you can evaluate, I could evaluate this, for example, in the first coordinate system. If I evaluate it in the second coordinate system, I get the same answer, or it doesn't matter. So what I'm trying to lead up to is I can do this product in the first coordinate system and this one in the fifth coordinate system if I want to. So I'm going to, when I do each of these dot products, I'm going to look at all 10 of my coordinate systems and try to find what looks like the simplest expression. So it sounds kind of crazy, but, and actually a lot of times what I do is I wrote down set 8 because we're doing a dot product with A34, and in set 8, A34 is simple, right? It's 1, 0, 0. I'm sorry, set 3, and in set 8, A34 was simple also. So I did those. So, okay, let's do all these dot products now. S1.A34. So I can either write X54 or X23. Doesn't matter. Because I know all the joint angles for the A and the B case. Hey, and then X54 better equal X23 or else we got some other problems going on. But if you go into our toolbox, it's in there. So it's like, holy cow, this stuff all matches up and always works. Okay, this dot product, A12.A34. If I do it over this set, I'm going to get W154. If I do it over here, I'm going to get W23. That seems simpler. S2.A34. Let's see, what do we got? Over in this set, I'll get X154. Okay. And in this set, I get X3. That looks simpler. Hey, but X3 better equal X154. It better be in our toolbox, or we got to work. It is, or else we'd have a world of hurt. Let me double check. 154. Oh, yep. That's actually a fundamental, but that's okay. Next dot product, A23.A34. So from this set, I get cosine 3. From that set, I get cosine 3. Well, yeah, it's the cosine of the angle between them, and theta 3 is the angle between them. S3.A34 went to Zippo 0 because they're perpendicular. Yep, and this one goes to 1, and this one went to 0. A45, A34. I have a choice. C4, right, the angle between them. S5.A34. I look in here, I've got either X4 bar or X123. Yeah, they better be equal, and they are. And A51.A34. I can get W54 or, yeah, that looks simpler. So this other way to attack this problem of getting the A and the B case of those joint offsets was to take the vector loop, and I decided to dot product every vector with something that made two of the unknowns disappear. So the equation that we have up there with everything's in purple, again, I'll take the given theta 5, the given theta 3, and the A case for all the other angles. And I will wind up with one equation in that unknown, and I'll get S2 the A case. I'll take those same two equations, I'll put in the given theta 5, the given theta 3, and then the B case angles, evaluate everybody, and get S2 for the B case. Okay, so instead of three equations, three unknowns, we have the S2 now, the A and the B. So what might I do with this next to get the other two offsets? I probably would do a dot product with, say, A23. If I do a dot product of all of these with A23, that one's gone, that one's going to be gone. Again, everything's with A23 now. That goes to 1. And again, I would have to pull out some different sets to get simpler dot products. And what I would wind up with is an equation that had that as the only unknown. And I would put in the A case angles and evaluate all the terms and get S4 for the A case, and then do the same with the B. And then lastly, we're missing one term, the S3 distance. And I'd probably do a dot product of everybody with S3. Just because that would go to 1, S3 dot itself. I've already got the A and the B case of those. So you kind of had this choice, take the vector loop equation, express every vector in a common coordinate system, which is what we did back here. I just picked set 1, and then A case, B case, all those vectors, solve three equations, three unknowns, or I played this dot product game and tried to get just one equation, one unknown, 3 times though, which is a pain. So we have solved, look at the clock here, so we have solved our first group 1 mechanism. So if you go back to this problem statement, yeah, we got the A case and the B case for all 6 of those parameters. I don't remember in the book if I drew, or if I did, I didn't show it. So we're going to do another one today. In the next class, we're going to look at, we're going to do a couple of reverse analyses. So that's where everything will come together. Okay, so in this problem, again, when we give the closed loop mechanism like this, the first R corresponds to this guy, and then I think, well, let me back off on that. Let's go ahead and look what we have here. I've got a revolute, revolute, prismatic, prismatic, revolute, prismatic, revolute. And so let's look at the mobility over here. So the mobility is the sum of the freedoms of the joints minus 6. There's 7 1-degree of freedom joints. So this is 1. And when we go to the equivalent spherical, I know theta 3. So I'm kind of showing that this is like welded together. I know theta 3. Let's see, what else? There's a prismatic at 2. So I know that one. And there's another prismatic at 5. So when I look at the mobility of the equivalent spherical mechanism, it's the sum of the freedoms of the joints that have mobility, minus 3. And there's 4 of them, right? I can see them. 1, 2, there's 4 of them that can move. 4 minus 3 is 1. So we have a 1 degree of freedom spatial mechanism whose equivalent spherical mechanism also has 1 degree of freedom. So it's a group 1. So we ought to be able to solve it in chapter 7. So it should be a relatively simple problem. And I'm checking the clock, and I think we're going to be just about right today. So I'm going to go ahead and erase this board, and we'll put this picture up there, and then put what are we given, what are we looking for, the whole thing. Okay, get rid of all that. Okay, so the picture, so we've got, that link is fixed, 7, 6, 5, 4, 3, 2, 1. And we've got revolute, 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 prismatic, revolute, prismatic, prismatic. Okay, so our given is alpha 1, 2 through alpha 7, 1, and A1, 2 through A7, 1. So we're going to know all the lengths. Oh, let's see. I also know over here where the prismatics are. I know theta 2, theta 3, and theta 5. And let's see, for the joint offsets, we're going to know where the revolutes are. We're going to know S7, S1, S4, and S6. It's a 1 degree of freedom device, so I have to give you one of the revolutes, one of the thetas. And today I'm just going to say theta 7. Okay, so that should be all the given. What are we looking for? It turns out there's always in these group 1s, there's going to be 3 angles and 3 distances. So the angles are theta 1, theta 4, theta 6. And then where the prismatics are, we need to get these offsets, S2, S3, and S5. So there's our problem statement. We're going to draw the planar representation of the equivalent spherical mechanism. Okay, revolute, there. There's a prismatic, so I know that angle, revolute. There's a prismatic, so I know those. Boom. Oh, I'm going to go ahead and say, all right, theta 7 was given. And again, in these group 1s, so we have a 3D spatial mechanism that has 1 degree of freedom, whose equivalent spherical mechanism has 1 degree of freedom. We're going to be able to solve for the A and B case joint angles right off the bat. So it's just a matter of who do we want to solve for first. I'm going to go for theta 1 first. So I'm going to say, well, Z7, yeah. 1, yeah, I want 1. Right, 7 was given. I want 1 because that's what I'm looking for. It's okay to put 2 because prismatic joint there. It's okay to put 3. If I could get 1 more into C, I'd have a fundamental law, but I don't want to put 4. So I'm going to stop. Turns out then it's a subsidiary, and 7, 1, 2, 3, Z5 or Z5 bar. Wow. So we went into the toolbox and found, just like we did in chapter 6, but we found the 1 equation and 1 unknown. Now when I expand this, I want to get it into A cosine 1 plus B sine 1 plus D equals 0. It's going to be easier if I take this equation, right, because the 1 will pop out sooner. Because by definition, Z7123 is identical to 3217. So if we expand this definition, we get a sine X S plus Y C plus a cosine Z. I'm going to say minus Z5 bar equals 0. And then we have to say where X321's definition is XC minus YS and Y321 and Z321. Right? They write out their definitions. And we have to substitute those in there, and we have to group all the unknowns together so that we will get it into this format of A cosine 1 plus B sine 1 plus D equals 0, where A, B, D will evaluate based on all the junk we're given all the alphas. Given those 4 thetas, yeah, the cap A, B, and D will evaluate to numbers. So right off the bat, our solution tree got theta 1A, theta 1B. And I'm just getting lazy today of expanding those and then substituting them in and grouping them, because I usually use Maple for that. I mean, this isn't too bad, right? It's just one substitution of this into there and regrouping, but okay. So the next thing we're going to do is to solve for the A and the B case for the other 2 thetas, theta 4 and 6. And we're going to look at those buddy equations again. Let's see. Boy, here they are. We're going to look at X7, 1, 2, 3, and Y7. Not that those are the only equations that would work. And then we're going to look at x3217. It's just, it always works, so I just go for it. Okay, 7123, if we look in the appendix, that's going to be x54 and negative x54 star. And 3217 is going to be x56 and negative x56 star. And the way that I'm doing that is I'm going, well, if it was Z3217, I had a Z5. So when it's the X, I take one more, 5, 6. I mean, that's how I'm doing it in my head. There's no real magic there, because you just look in the appendix and you'll find those. And again, when you expand this definition, we're going to get what the sine and cosine of theta 4 pop out. We're going to evaluate basically with these two equations, right? We get two equations, two unknowns. I'm getting lazier and lazier. I'm going to keep the chalk budget low today and not write as much. From those two equations, though, we will be able to get the corresponding value for theta 4a. And then from these two equations, when we expand them, you're going to get the theta 6 pop out. Sine and cosine of theta 6 are the only remaining unknowns. Because thetas 3, 2, 7, and 5 are given. And for the A case, theta 1 will turn into a number. And yeah, a lot of evaluation and stuff, but you can get two equations, two unknowns, and the sine and cosine of theta 5. Then we're going to go back to these two equations and put in the theta 1b and get the sine and cosine of theta 4b. Go back to these two equations, put in theta 1b, and get the sine and cosine. So, you know, based on what we did in Chapter 6, these Chapter 7 ones are pretty simple, these group ones, because we're doing the 3D spatial now. We're doing the 3D spatial, but again, the problem decouples where you get the joint angles first, and then, boom, get the distances. Okay, so now what's left for us is to get the corresponding A and B values of those, and it's going to be painful. Yeah, what you got?
Would that be theta 6, not theta 5?
Oh, would that be theta 6? Theta, yeah. Thank you. Yep, 6 was the unknown that was going to pop out, and I've been saying the wrong one. So it's funny, because a lot of times I think, like, if I was doing the video at home, I would go back and, like, pretend it never happened. But I bet you if I did that video at home, I wouldn't have noticed that I made a mistake. So what's left is to get these offset values, and you say, oh my goodness, it's not going to be fun, but it's going to be definitely doable. Let's see what I got on the PowerPoint, if I have anything that'll make life a little bit easier. Oh, here we go. Did I write them down? No, I didn't. So the one approach is to take the vector loop equation that should have like 14 terms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh yeah, there's 14 vectors if you walk around the loop of that mechanism. And I can express them all in any of the coordinate systems. And there's 14 of them in the appendix, so here's set 1. So I would have the S1 distance times 0, 0, 1, plus A12 times 1, 0, 0, plus S2 distance times 0 minus S12, C12, plus, 14 times, and it equals 0, 0, 0. So I could take that set, I could have used any of the sets, write those out, and we're going to have three equations in, then I have to, oh shoot, I hate it when it does that. Then we have to, once we substituted those in there, we need to evaluate all these terms for the A-case angles. And yeah, these vectors, because I know for the A-case all the angles, we are going to get the directions of numerically of all those vectors in the first coordinate system. It's a pain in the neck, and then what you wind up with is three equations and those three scalar unknowns. So a lot of work. You're writing the program, easy to make a mistake. Then I'm going to, after I've evaluated these all in the first coordinate system, I'm going to put in the B-case angles and turn everything into numbers and solve three equations, three unknowns for the B-case. Okay. Or, here's another way. I looked at this and said, you know, if I do a dot product with A23, I know that, oh, here we are, dot product, everybody with A23, I know that those are perpendicular. I know that goes to 1. Oh, no. I know that goes to 1, and I know those are perpendicular. So basically, I'm going to get a scalar equation in that only unknown. So again, I wrote down the sets here where A23 was simple, so the dot products would be simple, and you would evaluate like what coordinate system I want to evaluate those in. And you just, kind of what we did last time, except there's 14 terms, and I'm like, boy, I'm feeling really lazy today. Not really feeling like doing that. Then I would do the dot product again and put in, for when I evaluate all of the results of the dot products, I put the B angles in there, the B case, and I get the value for S5 for the B case. Then I might do a dot product with, I probably didn't even show it here, nope. I could do a dot product with A34, because I know that would get rid of the, I would have, I've already got the A and the B case of that, and I know all the A case angles in the B case, so I'd be able to solve for the A and the B of that. And then the last thing I'd probably do is a dot product onto S3, because that's the remaining one. And I know the A and B of everybody else. And that's a lot of work, but computers are pretty fast. It'll evaluate those two solutions pretty quick. Okay. So these group ones are pretty simple based on what we did. So, you know, when I look at the next exam, it's through chapter 7. There's not much in chapter 7 that's different from 6, except for this. When I go for those 3 joint offsets, it's a vector loop, and you either evaluate all the vectors in here, all the vectors in a common set, and A and B case them, and 3 equations, 3 unknowns, or you do this and start playing the dot product game to try to make it, but you're doing the same job. So, okay, so what are we going to do in the future? We're going to do 2 cases. We're finally going to get back and do a reverse analysis. So, you know, we went through all of the stuff in the book, and we're doing these spherical mechanisms, and we're doing, and how does this come back to the reverse analysis? So that's what we're going to do. So we're going to do a robot such that when we give it the desired position orientation and we close the loop, we're going to get a group 1 closed loop, you know, spatial mechanism, where in this case, I guess theta 7 is going to be known when we close the loop. And we're going to solve this one out. I was going to say, I don't remember if this one is in the book or not. Let me take a quick peek. I don't think it is, because there's something that's kind of coming back to me. So if I go to chapter 7, okay, so we did this just now. This mechanism 1 we just did. Yep. Okay, so the first one that we're going to do is not in the book, and I kind of wish it was. I wish I would have picked this as the first one. And we're going to find this to be a pretty simple problem. Given the desired position orientation of the end effector, right, we're going to close the loop, then that's going to turn into a group 1 closed loop mechanism. So the one I did in the book was, I said I wanted to go to a simplest case. And I said, well, this will be the simplest. Here's a robot that has 3 cylindric joints, but it does introduce some other weird thing, or different thing that we hadn't seen before. It has to do with the fixed coordinate system. So I think it would have been better had I done the example that we're going to do next. Oh. So I did not put this one in the book. Well, let's just set it up. We've got a couple minutes left. What's the exact problem statement? So again, we are going to know for these links, you know, A12 through A56 and alpha 1, because we know all the link stuff. And then we look up here, there's a revolute joint here. And again, there's no S1, right? That doesn't exist for the robot, so we never had that. There's a prismatic, so I'm going to know theta 4. Here's another prismatic. I'm going to know theta 2, and then here's another prismatic, so we're going to know theta 5. So those are all the constant mechanism parameters, the thing that, for, you know, when we build the table, those are the things that never change. Okay, then we're going to go ahead and make sure we've defined the coordinate system on the last body. So we had to pick this distance, and then we etched this line, A67, So if we were to zoom in over here, the green piece is what's spinning, and I've etched an A67 into there, that red line over there. And because I picked this distance, I knew where the origin of the coordinate system was. How far did I walk from A56 along the S6 vector, which I can see, to get to where my A67 is etched. Okay, so that's all the regular stuff. We got that coordinate system. And then it looks like on this problem, you know how normally I said there's a tool point known in the sixth? And we said, where do I want the tool point in the fixed? And we would back up and get 6's origin. I just skipped all that. I just said, I'll tell you where 6's origin, where I want it to be, and the direction of those vectors. So this is where I want that point to be in the fixed coordinate system. And here's the direction of the z and the x of that last. So basically, I'm given the position orientation. Find those 6 joint parameters. 3 angles, 3 distances. So this will be our first actual reverse analysis where everything's coming together, right? Based on all this given information, we're going to go ahead and close the loop. And when we close the loop, we're going to find that we have a 1 degree of freedom closed loop mechanism where we're going to know theta 7 is one of the closed loop parameters, and then we're going to go and knock that thing out. So it'll go pretty easy. Okay. So I say enjoy chapter 7 because it's easy, because when we get into chapter 8, it's a little harder. It's not terrible. And chapter 9s and 10 are the group 3s and 4s, and we're just going to look at them from an academic high perspective and say it's interesting what they did. I'm glad that they thought of doing it that way. But, you know, you're not going to, like, in an hour do it and you're on a test or something, because it was like somebody's PhD dissertation to get those knocked out. Okay. So y'all doing okay? I was having trouble keeping energy up today because it's like I said, it's the same old stuff, you know, over and over and over, it seems. Yeah, what you got?
For the 3 equations, 3 unknowns, what are the 3 equations?
Oh, the 3 equations.
One of them is
Gotcha.
all the vectors equal to 0.
Yep, because, so when we did it this way, so he's asking about, so this was the first one we did, this mechanism here. When we wrote the whole loop equation, it turned out there were 10 vectors, 5 S vectors and 5 A vectors. And these are the unknowns because that's where the prismatics were. I think they were prismatics. Or were they, a prismatic and 2 cylindrics. So when I wrote this equation, I know it has to equal the 0 vector, so it's 0, 0, 0. And one way to solve this was, what if I evaluated, in this case, I did all of the vectors in the first coordinate system. Oops. Come on. If I hide that, it wouldn't do that to me. If I evaluate, so here's the first coordinate system. So I just said, okay, S1 is 0, 0, 1. A12 is 1, 0, 0. And then the way that we're getting our 3 equations is, here's my unknowns. So the first equation is S1 times 0 plus A12 times 1 plus S2 times 0 plus that equals, 0, 0, 0. So when I take the top row, I get 1, and the middle row gives me another. Yep. The third row gives us the third. So, yeah. So either attack them that way, and then again, what's a hassle is we have to evaluate all of these for the A case angles. And solve 3 equations, 3 unknowns for the A case, and then we have to evaluate all of them for the B case angles. So there's a lot of work there, but it's definitely solved. It's all doable. Okay, so we're going to do reverse analyses. Next class, finally, we'll get back to those. So see you on Wednesday.
Oh.